Alaikum girls, I am Shamsunisa from Royal Degree College, Chemistry Department. As we are seeing the unit 3rd, Physical Chemistry in that Chemical Kinetics. Today we will study about some examples of first order reaction, pseudo first order reaction, second order reaction, problems based on second order reaction, examples of second order reaction, characteristics of second order reaction, zero order reactions, example of zero order reaction, characteristics of zero order reaction, and problems based on zero order reactions. We'll start with some examples of first order reaction. First example we are seeing here, that is decomposition of hydrogen peroxide. So the hydrogen peroxide will show the decomposition. It has been found to obey the first order rate law and can be represented as. Here you can see the equation H2O to the hydrogen peroxide. It will show the decomposition, and as a result of that we are getting water molecule plus one nascent oxygen. This step is a slow step. So in the next step we are taking the 2 moles of nascent oxygen. They are reacting, and as a result of that we are getting the oxygen molecule. This is the fast reaction. The progress of the reaction is usually studied by titrating equal portions of hydrogen peroxide against potassium permanganate at definite interval of time. So here the amount of potassium permanganate consumed is proportional to the hydrogen peroxide present at that instant, that is A minus X. Next example we'll see, that is the decomposition of oxalic acid. It follows first order kinetics. The reaction is, we are taking oxalic acid COOH single bond COOH. It will show the decomposition, and as a result of that we are getting carbon monoxide plus carbon dioxide and one water molecule. So the reaction can be studied finding out the concentration of oxalic acid at definite interval of time. So here in this case the decomposition of oxalic acid can be known by titrating it against standard potassium permanganate solution. So the volume of potassium permanganate used for each titration, it is directly proportional to the amount of oxalic acid present at that instant, that is A minus X. So here you can see the equation K1, it is equal to 2.303 by T log A by A minus X. Next we will see about the pseudo first order reaction. In a chemical reaction, when one of the reactants is present in large excess, the second order reaction conforms to the first order and is known as pseudo unimolecular reaction, or it is also called as pseudo first order reaction. Here we'll see the first example, that is hydrolysis of methyl acetate. So hydrolysis of methyl acetate in presence of a small amount of acid is an example of pseudo unimolecular reaction. Here in this the concentration of acid remains unchanged and it does not appear in final equation. Water is present in such a large excess that its concentration too remains constant. The reaction rate therefore is solely determined by the concentration of ester. So the process is of first order. Next example we'll see, that is inversion of cane sugar. Here you can see the reaction. We are taking sugar, sucrose, that is nothing but cane sugar. Its formula is C12H22O11. In that hydrolysis will take place, addition of water molecule. So as a result of that we are getting one molecule of glucose and one molecule of fructose. It obeys the first order rate law, as the amount of water present is in such an excess that its concentration may be considered to remain constant. The reaction is therefore a pseudo-unimolecular reaction. It can be studied by observing the optical rotation of the solution from time to time. As sucrose and invert sugar both are equimolar mixture of glucose and fructose, they have different values for specific rotation. Next we will see about second order reaction. If the rate of reaction, it is directly proportional to the product of first power of concentration of two substances or to the square of concentration of one substance, then the reaction is called second order reaction. We'll see the case 1, that is derivation of rate equation when two reacting substances are same. Here in the reaction you can see A is the reacting substance, that is the reactant. How many molecules of the reactant we are taking? 2. So both the reactants are same. They will react and as a result of that we will get the products. So initial concentration of A is small a and the initial concentration of the product is 0. So after the time t, the concentration of the product is x and the concentration of capital A is A minus x. For this reaction, a rate equation can be written as how dx by dt, that is change in the concentration of x with respect to change in time, it is equal to K2 molar concentration of A to the power 2. So here in the next equation, in place of molar concentration of A to the power x, we are writing the value of A, that is concentration of A after the time t is A minus x, isn't it? So that value we are substituting here, A minus x to the power 2. So here, bringing x term on one side, dx divided by, see here, this A minus x whole square we are bringing to the other side. So divided by A minus x whole square. It is equal to K2. This dt we are bringing to the other side. So K2 dt. Integrating on both sides. Integration of dx by A minus x whole square, it is equal to integration K2 dt. Now we are using this formula, that is integration of 1 by x square dx, it is equal to 1 by x. Okay, so here see that A minus x whole square is there now, that is nothing but x square. Okay, in place of that one we are writing what 1 by x. So 1 by A minus x, it is equal to K2, it is a constant, so we are taking as it is integration of dt. See here, integration of dt is t, so we are writing t plus c. C is the integration constant. It is our equation number 1. When t equal to 0, x equal to 0. So at that time in this equation 1, we are substituting the values of t and x. Okay. So here 1 by A minus x is there. Now in place of x, we are writing the value of x as 0. It is equal to K2, value of t is 0. So we are writing 0 plus c. So k into 0 is 0. So here we will get 1 by c here. A minus 0. A minus 0 value is a. So 1 by a it is equal to c. It is the value of c. C value is here what? 1 by a. Then substitute the value of c in equation 1. It is our equation 1. What is that equation? That is 1 by a minus x equal to K2t plus c. In that, in place of c, we are substituting the value of c as 1 by a. Then bringing a on one side. This plus 1 by a we are bringing to the other side. Okay, then we'll get minus 1 by a. It is equal to K2t as it is. Then this t we are bringing to the other side. So 1 by t. Then rest of the things are as it is. Then we are taking the LCM, guys. A into 1. So you will get a. Then minus. Then a minus x into 1. So you will get a minus x divided by a minus x a. It is equal to K2, isn't it? Now this a as it is we are writing in the next step. Then minus into plus minus a, then minus into minus plus x divided by a minus x into a. It is equal to K2 as it is. So minus a and plus a gets cancelled. So you will get here about x, isn't it? 1 by t, x divided by a minus x into a, it is equal to k2. Now this one, x into 1 is x only, isn't it? So our final equation will be like this, x by t into a minus x into a, it is equal to k2. This is the integrated rate equation for the second order reaction. Second case we will see here, that is derivation of rate equation when concentration of the two reacting substances are different. Consider the initial concentration of A and B are different, say small a and small b moles per liter. See here, see the reaction. A is one reactant whose initial concentration is small a at the time 0. Okay, and B is the another reactant. Its concentration will be small b. Small b is the molar concentration of capital B and small a is the molar concentration of capital A. And at the time 0, the product, as we are getting the product initial concentration is 0. Then after some time t, the concentration of the product x will be x, and the concentration of A is A minus x and concentration of B is B minus x. The rate equation for the above reaction can be written as how? Dx by dt, that is change in the concentration of x with respect to time, it is equal to k2 A minus x, that is the concentration of capital A and concentration of capital B after the time t, that is A minus x into B minus x. Now we are bringing this x value on the one side. So dx divided by a minus x into b minus x, it is equal to this dt we are bringing to the other side. So k2 dt. Integrating on both sides. So integration of dx by a minus x into b minus x, it is equal to k2 integration of dt. So the expression 1 by a minus x into b minus x can be written as like this. This formula we are following. That is, it is equal to 1 by a minus b into 1 by b minus x minus 1 by a minus x. Okay. This value, it is equal to 1 by a minus x into b minus x. Now, this value, see here, as this expression we are taking, this we are writing in place of dx by integration of dx by a minus x into b minus. So we are writing here integration 1 by a minus b into 1 by b minus x minus 1 by a minus x dx, it is equal to k2 integration dt. It is as it is. Now we are taking this 1 by, see, 1 by a minus b, it is for 1 by b minus x and as well as for 1 by a minus x. So we are taking this 1 by a minus b as common. So we are writing here. Okay. See girls, here this 1 by a minus b, it is kept as constant because in this x is not there, isn't it? So we are taking this as a constant and this integration we are splitting and we are keeping the integration before 1 by b minus x and as well as before 1 by a minus x. See, and here the dx is there, na? So this dx, it is multiplied with this also and this also. So we are getting integration of 1 by b minus x dx minus integration of 1 by a minus x dx. It is equal to k2 integration dt that we are getting. Now we are using this formula, that is integration of 1 by x dx, it is equal to minus ln x. Okay. So here in place of 1 by x dx, means this one is 1 by x dx, this one is also 1 by x dx. In that place we are writing what? Minus ln x. That one we are writing here. So this is constant now. We are keeping as it is 1 by a minus b. So into minus ln b minus x minus then minus ln a minus x, it is equal to k2 t. It is equal to k2 t. Now here in the next step, this minus into minus will become plus. So rest of the things are as it is. Then 1 by a minus b in the next step, 1 by a minus b. Then we are taking this one first. We are writing this one first. That is the plus ln a minus x. Then this one as it is we are copying. There is minus ln b minus x. It is equal to k2t plus c. That we are writing the c. It is nothing but integration constant. It is our equation number 1. So in the next step, we are using this formula for that. That is ln A minus ln B. It is equal to ln A by B. See here, this is ln A, this whole, and this is ln B. It is equal to what? Ln A by B means A minus X by B minus X. Ln we are keeping as a common. So 1 by A minus B into ln A minus X by B minus X. It is equal to K2 t plus c. It is our equation number 2. When t equal to 0, x equal to 0, then a minus x it is equal to, in place of x we are writing the value of x as 0. So a minus 0 equal to a. B minus x value again 0, so it is equal to b minus 0 equal to b. Now we are using this second equation. What is our second equation? 1 by a minus b ln a minus x by b minus x, it is equal to k2t plus c. In that we are substituting the values. That is a minus x value is a, isn't it? B minus x value is b, that we are writing. And the value of t is what? Here the t is considered as 0. So k2 into 0 is, it will become 0 only. What will remain? That we can see in our next step. 1 by a minus b ln a by b, it is equal to c. Substituting the value of c in equation 2. Now in equation 2, we are substituting the value of c. Our value of c is this one, girls. What is the value of c? 1 by a minus b ln a by b. That is the value of c. In that equation, we are substituting in our equation 2. So everything is same in equation 2. Only in place of c, we are writing its value as 1 by a minus b ln a by b. Now in the next step, what we are doing? This one. This value we are bringing to the other side. That is 1 by a minus b ln a minus x by b minus x. This is as it is. As this ln a by b we are bringing to the other side, so it is becoming negative. So we are writing here ln a by b. And then it is equal to k2t. Here the k2t remains, that the k2t we are using. And one more thing you have to remember here, this whole value. First of all, what will happen is 1 by a minus b ln a by b, this whole value will go that side. So this 1 by a minus b, here 1 by a minus b is common, na? So that's why we are keeping this value as common. Okay. Then we are using, in our next step, we are using this formula, that is ln a minus ln b. It is equal to ln a by b. See here, this one is ln a. This whole a minus x by b minus x is ln a. Okay. Then minus ln b. A by b is nothing but, what is a by b? Ln b, that one is. So ln a by b we are writing. Here the k2t as it is equal to 1 by a minus b ln a minus x by b minus x. This one is ln a. Okay. So this whole value a minus x by b minus x, this is a, and divided by a by b, it is whole is b. So a by b, ln a by b. Next is, in the next step, this one c. It is becoming reciprocal a by b. So we'll get here b in the numerator and a will go to the denominator. Now in the next step, this ln we are converting to the log value. So, and this particular t which is present on the left hand side of equal to b, we are bringing to the right hand side, so it will come in the denominator. So we will get this equation k2 it is equal to 2.303 by t into a minus b log b into a minus x by a into b minus x. So this is the second order rate equation when the two substances are here different. Now we will see the problem, girls. First problem we'll see, that is the 20% of a second order reaction is completed in 40 minutes. How much time will it take for completion of 80% of reaction. We'll see the solution. Given data is A is, what is A? Always the initial concentration will be, initial concentration of the reactant will be 100. So A is nothing but initial concentration that we are taking as 100. Then X is 20. That is the 20% of the second order reaction is completed in 40 minutes. How much time? 40 minutes. So we are taking this formula K equal to X by T into A minus X. So we are keeping the value in that formula. We are substituting the value. K equal to value of X is 20 divided by T value is 40 into A value is 100. Then in the bracket A minus X 100 minus 20. If we subtract this 100 minus 20, we'll get 80. See the next step. The 20 now from that 20 the 0 and from 80 0, both the zeros gets cancelled. 2 ones are 2, 2 fours are 8. Now 4 fours are 16. Here 0 is there, 160. 160 into 100. So you will get 1 by 16,000. It is the value of K. Now A equal to 100. That is initial concentration of the reactant is 100. When the concentration is here, when the reaction is completing at 80% reaction of, see here, you can see for completion of 80% of the reaction, it is asking to find out the time now. How much time it will take? Now you can see here, that is X value is 80. Here you are going to find out the time. K, it is equal to this formula we are using. In place of K, we are substituting the value of K in that equation. What is our formula? K equal to X by T into A minus X. So we are keeping the value of K as 1 by 16,000. It is equal to X value is how much? 80 divided by T. We don't know. You are going to find out that into A value is 100. Then 100 minus 80. A minus X. Now, so 100 minus 80. So you will get the value as, if you are subtracting that, you are getting the value as 20. Then we are cancelling both zeros. 0 0 gets cancelled. Then 2 ones are 2, 2 fours are 8, then 4 ones are 4, 4 twos are 8, 4 fives are 20. So you will get here T into 25, isn't it? 1 by T into 25 is equal to 1 by 16,000. Now we are finding out the value of time, T. So the T we are bringing to the other side. So this 16,000 will go towards this side, so it will come in the numerator. 16,000 divided by 25. If we are dividing this value, we will get the time is that is 640 minutes. So 640 minutes time, it is the time required for the completion of 80% of the reaction. Okay girls. Next we will see the second problem. The rate constant of a second order reaction is 3.33 into 10 to the power minus 2 mole inverse liter second inverse. Calculate half-life period of the reaction. Here he is asking to calculate the half-life period of reaction with initial concentration 0.05 moles per liter. So here the given data is the K value it is given. What is the value of K? K is nothing but rate constant of second order reaction. Its value is 3.33 in 10 to the power minus 2 per mole liter per second. Then A, initial concentration value is also given here, 0.05. Half-life period of the second order reaction, that we are going to find out. We are using this formula. T half it is equal to 1 by Ka. T half it is equal to 1 by, what is the value of K? 3.33 in 10 to the power minus 2 into A value is 0.05. Now, what we are doing, this point we are cancelling. So after the point that 2 digits are there, in place of 2 digits, we are keeping that 2 zeros above. Okay. And we are cancelling this point also. So the 2 digits are there after the point. Those 2 digits in place of that one, we are keeping the 2 zeros above. So here 10,000 divided by 333 into 10 to the power minus 2 into 5. It is there, isn't it? Now this 10 to the power minus 2 we are bringing to the numerator. So it will become 10 to the power 2 plus 2 that one. So 10 to the power 2 means 10 into 10, 100 that one is. 100 it is multiplied with 10,000. So you will get this value. Okay. Then 333 it is multiplied with 5. So you will get 1,665. Both this value we are going to divide. So you will get the T hop, that is hop life period, is how much? 600 seconds. Now the time we are converting from seconds to the minute. So 600, it should be divided by 60. At that time we will get how much time for the completion of a half life period of the reaction, that is 10 minutes. So if we are calculating the half life period in terms of minutes, you will get the answer 10. In terms of seconds, you will get the answer 600. Next, we will see about examples of second order reaction. First example you will see, that is saponification of ester. Hydrolysis of an ester by an alkali, commonly known as saponification of ester. Here you can see the reaction CH3CO, C2H5 we are taking, that is, it is named as ethyl acetate. C2H5 is ethyl, CH3CO is acetate. In that, hydrolysis reaction will take place in the presence of alkali. OH minus is alkali. So what will happen here? This C2H5 is coming out reacting with OH minus, and we are seeing ethyl alcohol, and acetate ion will remain, CH3COO minus. So the hydroxyl ion acts as a catalyst, but are used because they react with the acetic acid produced by the reaction. So if the alkali used is sodium hydroxide, the product will be sodium acetate and ethanol, and the rate equation is like this. Rate, it is equal to K, that is constant, molar concentration of ethyl acetate, molar concentration of OH minus. Next we will see about the decomposition of ozone at 100 degree centigrade. Now here we are seeing the second example, that is decomposition of ozone at 100 degree centigrade. We are taking the 2 moles of ozone, which is in the form of gas, and we are providing the temperature 100 degree centigrade. Then it will show the decomposition, and from that we are getting the 3 moles of oxygen gas. Here the rate of the reaction, it is equal to K, molar concentration of ozone to the power 2, because here the 2 moles of ozone we are taking, isn't it? It is the second order reaction. Next is hydrogenation of ethylene to ethane. We are taking ethylene, in that hydrogen is added, hydrogenation reaction will take place, and we are getting C2H6, that is ethane. So here the rate of the reaction, it is equal to what? K, molar concentration of C2H4 and molar concentration of H2. Nothing is there before C2H4 means 1, isn't it? So molar concentration of C2H4 to the power 1, H2 to the power 1. So 1 plus 1 means again you will get the value as 2. So this is the again example of second order reaction. So the rate of the reaction, it will be depends on the concentration of here ethylene and as well as hydrogen gas. Now we will see about the characteristics of second order reaction. The first one we'll see unit of second order rate constant. As we know, the formula of second order rate equation is K, it is equal to x by T into A minus x. Now in place of x, A, T, we are substituting its units. So the x is moles per liter, units of x. Unit of T, as it is, first of all we are writing, then unit of A is moles per liter, unit of A minus x, that is moles per liter that we are writing. So moles per liter gets cancelled. So here we'll get units of K, it is equal to time into mole to the power minus 1. It is becoming reciprocal. Then time to the power minus 1. It is also becoming reciprocal. Or once again see this units of K, it is equal to liter, see here, liter, it is becoming reciprocal, okay, into mole, it is going to the numerator from the denominator, so mole inverse. Then time, from denominator it is going to the numerator, so time to the power minus 1. Now as we are seeing the time unit of time we can take in seconds or minutes. If we are taking in seconds, second inverse, or minutes, minutes. Rest of the things are as it is. Next is the half-life period of a second order reaction. It can be evaluated by substituting x equal to a by 2 and t equal to t half in the second order rate equation. We are taking the second order rate equation, that is k t is equal to 1 by t into x by a into a minus x. Now the k it is equal to, see here, 1 by t is there. Now in place of t we are taking the value of t as t half into, in place of x the value of x is a by 2, that we are writing divided by a as it is, then into a, nothing is there in the denominator means consider here 1, then minus what is the value of x, a by 2, that we are writing. We are taking the LCM, that is 2 into a you will get 2a minus 1 into a is a divided by 2. Rest of the things are as it is. Now 2a minus a you will get a by 2, isn't it? So a by 2 gets cancelled. Then here k it is equal to 1 by t half a remains, isn't it? Now we don't know the value of t half, that we are bringing to the other side, so the k will go to the denominator. So t half it is equal to 1 by ka. Thus the half-life period of a second order reaction is inversely proportional to its initial concentration. Next we will talk about evaluation of k, that is rate constant, from graph. The value of k is determined by the graphical method, in which x by a into a minus x is plotted against the time interval t. Then a straight line is passing through the origin, will be obtained here. So the slope of the straight line is equal to second order rate constant k. Now you can see this, k it is equal to x by t into a minus x. This is the second order rate constant. This is the equation for whom? For the second order rate constant. Now this t we are bringing to the other side. So next equation is the kt is equal to x by a into a minus x. So here solving right hand side, this one, x by a into a minus x, first of all we are solving this side. Okay, adding and subtracting a in the numerator first of all. So plus a minus a plus x divided by a into a minus x. Then taking minus common. Okay, so here a minus, here a we are writing, then minus x. The plus will become minus x. Then divided by a into a minus x as it is. Now we will break the division sign. So we will get the next step like this, a by a into a minus x, then minus a minus x by a into a minus x. Now a gets cancelled, a minus x gets cancelled, so we will get 1 by a minus x, it is equal to 1 by a. Now this is the value which we are keeping in place of x by a into a minus x. Okay, you can see here. So the k, now what we are doing, k we are keeping on the same side, the t we are bringing to the other side, so 1 by t, this rest of the things are same. See girls, this is the equation of rate constant for the second order reaction. Now we are going to calculate slope with the help of this formula, that is kt plus, see here, kt, this whole value we are bringing to the other side, that is kt plus 1 by a, it is equal to 1 by a minus x. Now this one as it is we are writing, we are reversing this equation. Actually everything is same, 1 by a minus x, it is equal to kt plus 1 by a. This is in the form of y equal to mx plus c. So here m is slope and c is intercept. See here, y, the value of y is 1 by a minus x, it is equal to mx is kt, k is slope there, and plus c value is 1 by a, that is intercept. Graph can also be plotted between 1 by a minus x versus time t. A straight line with 1 by a here. A straight line with 1 by a as intercept and slope equal to second order rate constant, that is k. When two reactants are different, the graph can be drawn between 2.303 by a minus b log b into a minus x by a into b minus x versus time. It is a straight line. The slope of the line will give the value of k. Now we are going to study about zero order reactions. These are the reactions whose rate do not depend on the concentration of the reactants. See the reaction. A is the reactant. From this we are getting the product. So initial concentration of capital A is small a and the initial concentration of the product is 0. After the time t, concentration of the product will be x and concentration of capital A is a minus x. The rate equation can be written as dx by dt, that is change in the concentration of x with respect to change in time, it is equal to k naught a minus x to the power 0. A minus x is what? That is the concentration of A after the time t. So a minus x to the power 0 will become 0 only. So we are writing here it will be, see, anything to the power 0 is equal to 1. So we are getting here 1. 1 into k0, it is equal to 1. K not only. Now in the next step, dx by dt, it is equal to, as we have already seen this one, dx by dt, it is equal to k naught a minus x to the power 0, it is equal to k0, that is k naught. How? Anything to the power, just now I have explained, anything to the power 0 is equal to 1. So this value will become 1. 1 into k0 is equal to k0. Now dx we are keeping on that side only, dt we are bringing to the other side. So our equation will be dx equal to k naught dt. K0 or K naught, it is equal to 0 order rate constant. That is nothing but 0 order rate constant. Taking integration on both sides. Integration of dx equal to K0 integration of dt. Now x it is equal to, see, integration of dx equal to x. We all know this. So in place of integration of dx we are writing x. It is equal to k naught, as it is we are writing integration of dt is equal to t. So that's why we are writing t plus c. C is nothing but integration constant. It is our equation number 1. When t equal to 0, x equal to 0, in the above equation we are substituting the values. X value is 0, so we are writing 0, it is equal to k naught, as it is we are writing t value 0 plus c. So k0 into 0 means k naught into 0 equal to 0. So here remains only c. So 0 it is equal to c, or we can write c equal to 0. Substituting c equal to 0 in equation 1. What is our equation 1? X equal to k0t in k0t plus c, isn't it? So here x equal to k0t plus c. C is there, in place of c we are writing the value of c as 0. Now what will be there in the next step? K0t plus 0 is k0t only. So that's why we are writing the same. Now in the next step, we are bringing t to the other side. So x by t we will get, it is equal to k0. Or we can write in this way also, k0 it is equal to x by t. So this is called zero order rate equation. Now examples of zero order reaction. When rate of reaction is independent of initial concentration, it depends on some other factors like intensity of absorbed light in photochemical reactions or the area of catalyst in certain surface reactions. First of all, we'll see about the photochemical reactions. Means in the presence of light, the chemical reaction will take place. Combination of hydrogen and chlorine in presence of light to give hydrogen chloride. It is the best example for zero order reaction. You can see the reaction. hydrogen gas, 1 mole of hydrogen gas reacting with the 1 mole of chlorine gas. Reaction will take place in the presence of light and we are getting the 2 moles of hydrogen chloride. Second example we'll see heterogeneous reaction. Decomposition of hydrogen iodide on the gold surface. See here how the decomposition of hydrogen iodide will take place. 2 moles of hydrogen iodide on the gold surface, it will decompose and as a result of that we are getting 1 mole of hydrogen and 1 mole of iodine. Next is decomposition of ammonia on tungsten, molybdenum or platinum surface at high temperature. Here you can see the reaction. 2 molecules of ammonia on the platinum surface, or we can take the tungsten or the molybdenum surface. Ammonia will show the decomposition, and as a result of that, we are getting 1 mole of nitrogen and 3 moles of hydrogen gas. Next is characteristics of zero order reaction. The first one we'll see unit of K0. K0 it is equal to x by t. We know this formula, isn't it? It is the zero order reaction. It is the equation for zero order reaction. So now we are taking the unit of x. We are writing that is x unit is moles per liter divided by time. Okay. So here the unit of K0 is what? Moles as it is liter. It is becoming reciprocal. Okay. So look at this once again. The K0 it is equal to moles. This liter it is there in the denominator. It is going to the numerator. So liter to the power minus 1. Then time to the power minus 1. Time we can take in seconds or minutes. So second to the power minus 1 or minutes to the power minus 1. Half-life period of zero order reaction that we will see. Time required for half completion of reaction for a zero order reaction can be calculated. See the formula K0 equal to x by t. We know this formula. That is the value of x is we are taking as a by 2 because a is nothing but initial concentration. Here we are talking about the half-life period of the zero order reaction, half. So initial concentration will become half. So we are writing a by 2. Okay. When t equal to t half, then that K0 it is equal to, we are substituting these values in the above equation. In place of x, we are writing the value of x as a by 2. Then in place of t, we are writing the value of t as t half. So what you will get here, this t half we are bringing to the other side in the next step. It will be equal to K0, it will go to the other side in the denominator. So it will become like this, t half it is equal to a by 2 K0. Thus, half-life of a zero-order reaction is directly proportional to the initial concentration of the reactants. Next one is evaluation of K. A plot of x against time will give a straight line passing through the origin. The slope of the straight line will be equal to K0 or K0. So, our equation, our formula is K0 equal to x by t. Now, this t we are bringing to the other side. So, x will be equal to K0 t. Now, we will see the problems. The first problem is, in a zero order reaction, the initial concentration of the reactant is 0.2 m and half-life period is 100 minutes. Calculate the rate constant. Here we don't know about the rate constant. Here we are going to calculate the rate constant. So in the solution, given data is A, initial concentration is what? 0.2 m. Half-life period is 100, isn't it? 100 minutes. Zero order half-life period is T half, it is equal to A by 2 K naught. This is our formula. Then K naught, we don't know the value of K naught, isn't it? It is only to be calculated, rate constant for the zero order reaction. So we are bringing K naught to the other side. And the T half we are bringing to the other side. So our formula will become like this. K naught equal to A by 2 into T half. Now we are substituting the values. In place of A, we are substituting the value of A as 0.2 divided by 2 into T half. In place of T half, we are writing 100. Then here 0.2 is there. Now we are cancelling this point. This point, in case of that point, one digit is there after the point, so 10 we are keeping down. So it will become 1000 now. 2 gets cancelled, so 1 by 10 to the power 3. Or we can write in this way also, k naught, it is equal to 1 into 10 to the power 10 to the power 3 will go to the numerator, so it will become negative. So 10 to the power minus 3, mole liter to the power minus 1, unit to the power minus. Second problem we'll see. 30% of a zero order reaction is completed in 40 minutes. How much time will it take for completion of 90% of the reaction? Okay, here we are going to calculate the time required. So for the completion of 30% of the reaction, how much time taken? 40 minutes. And for the completion of 90% of the reaction, that how much time it is required, it is in required, or how much time will be required, that we are going to calculate. Zero order rate equation is k naught equal to x by t. X is directly proportional to t, isn't it? So x1 by x2 it is equal to t1 by t2. This formula we are using. X1 is what? 30 divided by x2 is 90. It is equal to t1 is 40 divided by t2. We don't know the value of t2, isn't it? That we are bringing to the other side. So it is becoming reciprocal then, if it is coming to the other side. So 90 by 30 into 40. Now 0 gets cancelled, then 3 ones are 3, 3 threes are 9, 0. Then 30 into 4 you will get 120. That is that T2. Its value is 120 minutes. Thank you for listening my lecture.